Hi guys, welcome to the channel. So today we are going to talk about the topic of solvent effects. So in UV visible spectroscopy, or particularly in UV spectroscopy if we talk about, then we use the type of solvents which do not get absorbed in that particular range of UV visible, or you can say UV. Okay, we will take UV visible 200 to 800. So whenever we are taking some spectra of any given molecule, then we are going to use some sort of a solvent. And how we are going to choose a particular solvent? We have to choose that solvent which itself does not get absorbed in that particular range. For example, there are some solvents like CHCl3, carbon tetrachloride, and benzene. These solvents get absorbed in the range of 200 to 400 nanometer, that is UV range. So if we want to take a spectra of a molecule in this UV range, we will rather not use these type of solvents. For example, benzene gives absorbance at 255 nanometer. Carbon tetrachloride gives absorbance at 265 nanometer, and CHCl3 gives absorbance, that is chloroform, it gives absorbance at 240 nanometers. So whenever we are going to take the spectra in 200 to 400, that is UV range, we will try to ignore these type of solvents. Now what type of solvents we can use? Solvents like water, like methanol, 95% ethanol, and hexane also for that matter. We can use these type of solvents whenever we are taking the UV spectra, just because they do not get absorbed in this particular region, so they are not going to interfere with the absorption pattern of the molecule under investigation. Now the next question arises is, what happens if we take spectra of a molecule in different solvents? For example, we have a molecule and we want to take the spectra of that molecule in water as a solvent, in methanol as a solvent, in benzene as a solvent. Now not benzene, hexane as a solvent. So one case could be that molecule has a solvent of water, other could be molecule has a solvent of methanol, and third could be that the molecule has a solvent of hexane. Now what will happen in the spectra? What are the differences which we are going to observe in the spectra when we are going to use different solvents, which are of course not going to interfere in that range, but what changes we are going to observe? So we are going to discuss that point in elaborate way. Okay, so let's start with the solvent effects. So we were discussing that what happens when we take the spectra of a same molecule in different solvents. So for example, if we have one molecule for which we want to take the spectra, but we take two different spectras using two different solvents, that is we take this molecule and we take two of the solvents. For example, we take two solvents, one is ethanol and the other one is hexane. Okay, one polar and one non-polar solvent. So then we take the spectra. When we take some molecule in ethanol, then we take one spectra, and then we take that molecule in another solvent and we take the spectra. We take two different spectras, right? Absorbance and wavelength, absorbance and wavelength. So what are we going to observe in these two spectras? So for example, I have taken a molecule and I have taken the spectra of that same molecule in ethanol and in hexane. I am getting two different spectras and I have overlapped those two graphs. So one graph is like this and the other one is like this, right? These two graphs I have got. Now I have to tell which graph is for the ethanol as a solvent and which graph is for the hexane as a solvent. So first of all, we need to look at the interactions which will be happening inside that overall solution. So suppose we have taken ethanol. Ethanol is C2H5OH, right? It is a polar molecule. This is your solvent. Now suppose that molecule is having a carbonyl bond. Now what happens? This hydrogen and this oxygen, they start to interact via hydrogen bonding, right? Via hydrogen bonding. Now these interactions will be what? These interactions will be solvent, this solvent and this solute interactions, right? Now due to these solvent and solute interactions, what happens to the peak? The peak becomes broader, that is, we do not get these sharp peaks. So that is why in case of ethanol as a solvent, due to these type of solvent solute interactions which are happening, that is the hydrogen bondings which are happening, we get a spectra which is giving broader peak. So this will be the spectra with the ethanol, and the one with the sharper peaks will be the spectra with the hexane. Why? Because hexane is a non-polar molecule, and with hexane there is no possibility of solvent solute interactions, right? So now we will understand about this effect on the bonds. So what one thing we have to consider here is that the effect of this solvent, the effect of the solvent is only on polar bonds, right? Polar bonds, like carbonyl bonds we have taken, these are like polar bonds, these are polar bonds. So solvent effects are only valid on the polar bonds and not on the non-polar bonds, not on the non-polar bonds like C double bond C. These are non-polar bonds. On this, solvent solute interactions will not happen, and hence solvent effects will not be valid. We will get the same spectra with ethanol also and hexane also. So now in the next video we will take the alpha beta unsaturated compound, and then we will look at the two different types of shifts, that is N to pi star and pi to pi star shifts. We will look for the alpha beta unsaturated compounds and what happens to the N to pi star and pi to pi star shifts in those type of compounds when we take different solvents. Okay, so this will be the next topic that we will take up in the next video. So far that's it for this video. Thank you so much for watching.